We already know that using percentiles and quantiles allowing us to investigate what's going on in different intervals of the values. Now we are going to learn another way to do that, that works in a slightly different, from a slightly different angle. It's called distribution of frequencies, and later we will also talk about density distribution. Okay. The frequency distribution is a very simple thing. It tells you how often value falls into a particular subinterval of the whole range of the values. For example, if we have some values like this, so let's say it's some weight, and then we have, for example, these values here and this value here. Okay, so we have 4 values. To calculate quantiles, we need to split the all values into equal portions. So in this case, for example, if we want to split all values into 2 intervals, so we have to do it like this. So we have 50% of the values here, and then we have 50% of the values here. Okay, but the intervals of the values will be, of course, different. So we have this interval and this interval, so you can see that this is much bigger than that. So that's what we do in percentiles and quantiles. In the frequency distribution, we do another thing. So if we have the same values, 3 values here and 1 value here. So instead of splitting values into equal portions, we split the interval into equal beans or subintervals. So we take the whole range, so this is the max value, we take a little bit larger than this one, and this is the mean value, and split it into 2 equal intervals like this. So we have the length of the interval or subintervals is the same, okay? And then we simply count how many values we have in each. For example, here we have 3 values and here we have 1. We can also normalize, so we can divide all values into the total number of values. For example, here we will have 3/4 and here we'll have 1/4. So it means that 75% of the values are located in this subinterval, and then 25% of the values are located in this subinterval. So that's what frequency distribution is. So once again, the idea is following. First of all, we take the full range, the whole range of all values, and divide it into several subintervals. We will call them beans. Sometimes they're called breaks, sometimes they're called segments. We will call them beans, okay? And then for every bean, we count how many values are inside this bean. And then sometimes we can also normalize, because then we can compare different distributions when we normalize them. So we get, instead of the real number of values, we get percent. So that's what frequency distribution is. Let me show you an example. Let's say we have, again, 10 glasses of water, and then we measured a chloride content in these 10 glasses. So we ended up with 10 values like shown here. And we would like to make this frequency distribution, to calculate the frequency distribution. Okay. Well, first of all, we decide how many beans to use. That's a bit tricky question. I will talk about it later. So far, let's take 5 beans. So we would like to take the whole range and split it into 5 equal portions, 5 equal beans. Okay. Then the range. The minimum value is 53. It's this one. And the maximum value is 81.5. It's this one. So that's the range. But I would like to take a little bit wider. So let's say I will take 52 and 82, just to make the splitting a little bit easier. So that will be our range. We know that the length of this range is 30, 82 minus 52. So if we would like to get 5 beans, it means that the length of each bean will be 6 milligrams per liter. Okay. Now I can make a table like this. So these are the boundaries for each of the interval. And then we have some values. For example, why we have 1 here? Because we have exactly 1 value between 52 and 58. So we have only 1 sample with concentration of chloride between 52 and 58 milligrams per liter. And then we can find it. It's this one, of course. So this is the 53. Okay. Then we have 3 values here. Why it's 3? Because we have exactly 3 glasses of water with concentration of chloride between 58 and 64. We can find them. It's this one, and this one. Okay. So and so on. So this is called frequency table. Okay. Now, what to do if you have, for example, exactly 64 or 70? The idea is following. The lower boundary is a part of interval, but upper boundary is not. So what it means? For example, if we have something like 69.999 and a lot of nines, it will be still the part of this interval. But if we have 70, then it goes to the next. Okay, so the lower boundary is a part of interval, but the upper boundary is not. It's a part of the next interval. This is why the range should be a little bit wider than the real range. In this case, I made a frequency table as it usually is represented. So we have the bins here and the boundaries. Then we have this is the real frequency. And here I also calculated the relative frequencies. So in this case, we have 10 values, so it's quite easy. I just have to divide the values to 10. Okay. The relative frequency, as I said, it tells how much values you have in percent in each bin. So in this case, it's 10%, for example, and 30%, and so on. Okay. Well, how many bins? Well, that's a tricky question because there are no rule of thumb for that. In many softwares, they use this, it's called Starcher's formula, where n is a number of values, and then they take logarithm with base 2, and then plus 1. For example, if n is equal to 8, then this logarithm, the logarithm with base 2 of 8 is 3, so the total number of bins will be 4 because we add 1. Okay. But most of the time, you just need to play a little bit and see which bins represent the data best. But in this case, it's better to use a plot, a visual representation of your frequency table that is shown here. Okay, this plot is called a distribution histogram, and it's just a bar plot. The width of the bar is the same as the width of the bin, and the height of the bar is either the real value, or in this case, in the second plot, the height of the bar, it's a relative frequency. You can see that it doesn't, for visual purposes, it doesn't matter which to use because the shape is absolutely the same. But you can see that, for example, we have different scales. So we have 1 here and we have 0.1 here because it's a relative frequency. Sometimes, instead of the histogram, we can also use a sort of a polygon or a curve, like I've shown here. So you just take several line segments that crosses the middle points of your bars, and of course, if number of bins is relatively small, like we have, it doesn't have any advantage to use a curve instead of histogram. But if number of bins is large enough and the distribution is more or less smooth, then curve can be also a good representation of that. Now, I must tell that histogram is very good if you have enough values. If sample size is small, the histogram can be a little bit sort of misleading, so it will not tell you exactly the shape of your distribution. I used to say that if your sample size is small, you still can use histograms, but don't trust them. Okay, let me show you a couple of examples. In this case, we have our sample. Its sample size is 10, and that's how it looks like. Okay, this is the same sample taken from the same population, but now sample size is 30. So the idea is it should have more or less the same shape, but you can see that the shape is different. Okay, then I take another sample with sample size 100. Still, you see the shape look a little bit ugly or awkward. And this is the sample size 1000. Now you can see that the shape seems to be symmetric. It looks like a bell, right? So all these samples are taken from the same population. All these samples are random samples. But there is a clear difference in the shape of the histogram. Therefore, once again, use histograms, but very carefully. You need some experience in order to assess the shape of the histogram properly. And I'll show you the population, the histogram for the population. So in this case, we have 10,000 values. It's like 10,000 glasses of water. And then you can see the shape is very smooth and it's very symmetric. And if you compare the shape with the samples, only 1,000, where we have 1,000 values seems similar. Maybe a little bit with 100 values, this one. But the other two, well, far from to be the same. Okay. Another useful statistic is a cumulative or accumulated frequency that can be calculated as following. It shows how many values you have in this bin and in all bins with the smaller values. Let's take the first bin. We have this one. So we have the relative frequency for this bin is 0.1, and we don't have any bins with smaller values, so it will be also a cumulative frequency for this bin. If we take the second bin, the relative frequency is 0.3, and we have one bean with smaller values whose relative frequency is 0.1. So we just add it. And that will be the relative frequency for the second bean. And then for the third bean, we also take the real relative frequency and the relative frequencies of all beans before. So it will be plus 0.3 and plus 0.1. Okay. The relative frequencies are usually represented by a curve that is shown here. And you just simply take the points with relative frequencies and the values and connect them with lines. For example, if we take like 55 with this one, then its relative frequency is 0.1. Okay. You can think about relative frequencies as a sort of the same thing as a percentiles, but it's not for values, it's for beans. If the bean size is one value, then it will be the real percentile. But if the number of values is big enough, then the relative frequencies are a very good representation of the percentiles. So for example, if you take, I don't know, 60, this is 60, and then you can see that you have a cumulative frequency for the 60 is about 0.35. So it means that you can think about 60 as a 35th percentile for your data. Okay. And then if you compare the relative frequencies with the cumulative frequencies with the relative frequencies, you can think about relative frequency as a combination of all height of bars to the left. For example, for this bean, the relative frequency, it's the height of this bar plus height of this bar plus height of this bar, because it's exactly on the left we have the smaller values. So we have learned 3 new statistics that describes behavior of data in different parts of the whole interval of the values. It's a frequency distribution. It's also, you can also calculate the relative frequencies and the cumulative frequencies.